All right, welcome. This is section 7-2 on exponential decay, and thanks for tuning in. I think watching this video will certainly make the assignment we do in class tomorrow much, much easier. Now, you already know a little bit about exponential growth, and you know that we model exponential growth with the following. 1 plus r to the t. And, of course, a represents the initial amount. How much did I start with? A lot of times we talk about money with that. R is the rate. Because I am, with exponential growth, I'm growing by a fixed amount, 10%, 20%, whatever. And then t represents time. So I'm growing 5% per year for 10 years, and time is 10. And this is our growth model, growing by a fixed percentage. Decay is very similar, except instead of going up, we're going down. Growth and then decay goes the other way. And so because it's very similar, the model is very similar. And it starts out very much the same. Y equals A. And instead of 1 plus r, it's going to be 1 minus r. So to the t. So everything's the same. R is still the rate, called the decay rate now, not the growth rate. T is time. A is still the initial amount. The only difference is we're going down by a percentage, not up. And so this is called exponential decay. So to put this in some context, let's look at an example, because most often exponential decay is talked about in the context of an item losing value. Probably you know this most frequently from the idea of a car depreciating. Cars go down in value fairly quickly, and in fact, if you want to know the value of your car, you can go to kellybluebook.com and you'll input the age of your car, and it'll give you a rough estimate as to what it's worth, and it uses this math of exponential decay to come up with those numbers. So anyway, in this problem, I have an $8,200 snowmobile, and it decreases 20% per year. And the first thing we're going to do is write an exponential model. So we know that the exponential decay model looks like this. This is just the same thing I wrote previously, 1 minus r to the t. And we'll fill in our information. The initial value of my snowmobile is $8,200. 1 minus and 20% as a decimal is 0.2 raised to the t. And this is pretty good. Well, I think we'll simplify what's in the parentheses, 8,200. And 1 minus 0.2 is 0.8 to the t. And that's a pretty good general model. And when we talk about any exponential function, the input is the exponent, and I can input whatever number of years I want and find out what my snowmobile's worth. And so follow-up question, what's it worth after 3 years? Well, I can just take my model here, 0.8, and this time I am going to input a 3 to it. I'm going to input a 3 to it because that's the number of years I want. And if I input that on my calculator, let's see, 8,200, 0.8 to the 3, I can find out that my snowmobile after 3 years is worth $5,588.07. $5,588.07 is what I'm worth after 3 years. So we got a model. We use the model to see what I'd be worth after 3 years, and we can get a little bit better picture of this if we graph it. And to graph it, I am just going to punch it into my y equals and look at my table, or I could compute a few more of these by hand. But let's relabel our axes right here. This will be the number of years, and we can probably leave that as year 1 through year 8. That's fine. And we'll make the y-axis here dollars. But why don't we think of these instead of $1 through $8? How about we do $1,000, $2,000? You get the idea, all the way through $8,000. So this will just be the number in thousands of dollars. Now, I already have a couple of points here. I already know that at the beginning the item is worth $8,200. So let me drop a dot there right above 8,000. And I also know after 3 years we found out it was worth $5,500. So let me plot that 3 and then right in between 5 and 6. And let me get a couple more here. At 4 years it is about $3,300. So that's right here. And at 5 years, it's 2,600. So that's about here. And at 6 years, it's 2,100. So that's about here. And at 7 years, it's about 1,700. So that's about here. And at 8 years, it's about 1,400. So about here. And if we sketch the curve, we'll get something that looks like that. And what I want you to notice is this is the exact opposite of, say, exponential growth. Exponential growth would look like this, right? We'd go up, and this is the exact inverse of it. Okay, we're decreasing, not increasing. So there's our graph. Now, then it says, all right, let's use this graph to estimate when the car will be worth $2,500. So here I am at 2,500 right here, and let me just look over. I'll go right there and go right down, and it looks like, and this is just a rough estimate, and how accurate we are is going to depend on how carefully we graphed, but I would say safely between 5 and 6 years. Okay, just by looking at the graph, and we could do other problems with that. Okay, now last question related to the graph. According to our model, will the value of the snowmobile ever be worth $0? And there's a couple of ways we might approach this. It would be nice if our graph went out a little farther. Maybe we could look at it and see if it ever gets to 0. But let's try some numbers here. So you can just use your calculator for this or whatever. But you know, we've got out to 8 years. I wonder what it would be worth after like 20 years. So what if we did, you know, y equals 8,200.8 to the 20. I wonder what we would get. And I get that after 20 years, according to this, it's still worth about $94. Okay, and some change. How about 50 years? I wonder if it's worth 0 after 50 years. So I'll enter a 50 in my calculator. Boy, after 50 years, it's not worth a lot. I get 11 cents. So it's getting less as we keep decreasing here. Let's try a couple more. How about 75 years? Okay, I get approximately $0.00044. Gosh, that's not even a cent, right? That's less than 1 cent. But it's still not 0. And I think what we'll find here is we're going to get very close to 0, but never reach it. So that's one of those asymptotes that we talked about. If we were to make the graph of this and we were to extend it out, you would see it look something like this, where it would get very, very close and almost touch 0, but never quite get there. And maybe that's a good model, maybe it's not. Maybe the snowmobile will eventually be worth $0, maybe it won't be. But at least according to our model, it will never reach it. And that's an asymptote. It's that line that it gets very, very close to, but never crosses. Okay, so that's the basic idea with decay, and you'll have some problems like that in your assignment. But there's one more thing I want to mention before we wrap it up here, and that is how can you tell whether an equation is growth or decay? And let me give you a couple example equations. So let's say I gave you, and I don't know what this models, it doesn't matter, but 200 and 0.9 to the t, or letter B, y equals 200, 1.2. to the t. Now, one of those is growth and one of those is decay, and the question is which is which. In other words, I want you to be able to look at an exponential equation and know, yup, it's growth, or yup, it's decay. I want you to know. And the key to that comes from the model. So the exponential growth model, right, is 1 plus r to the t, right? So I add the rate to 1. Now, if I add some number, some rate to 1, so I'm taking 1 and I am adding something, then I should end up with a number that is bigger than 1. So let me say that again. If I take 1 and I add something to it, I should end up with a number that is bigger than 1. So if you look at these two, only one of them has a number bigger than 1. And so this is growth. Now on the other hand, if you have exponential decay, remember the decay equation is almost the same, but it's 1 minus r to the t. Now, if I take 1 and I subtract something from it, like 1 minus 0.1, I am going to end up with a number less than 1. So 1 minus a number gives me something that is smaller than 1. And so I'm looking for, right here, that's smaller than 1, therefore that must be decay. All right? And so I just want you to be able to recognize it, because I think being able to recognize whether an equation is growth or decay goes to you understanding what growth and decay are. And so with decay, since I'm subtracting from 1, I should end up with something smaller than 1. And with growth, I am adding to 1, so I should end up with something bigger than 1. Is basically how that works. And so you'll have a few in your assignment where you have to look at it and decide whether it's growth or decay. So that's it. Thank you for watching again, and we'll see you in class tomorrow.